Okay, this is a test. A proposed steam power plant design consists of an ideal Rankine cycle with reheat and regeneration. Steam enters the turbine 1 at P1 and T1 at a rate of M1 and exits at P2. A fraction, Y prime, of the steam exiting turbine 1 is diverted to an open feed water heater while the remainder is heated to T3 before entering turbine 2. The condenser operates at P4. Saturated liquid exits the condenser and is fed to pump 1. The inlet of pump 1 is fed into the feed water heater. Saturated liquid exits the feed water heater and is fed to pump 2. All turbines and pumps are isentropic. All right, well, let's begin by trying to sketch out the components. And, get a sheet of the homework over here by the sketch pad. Try and get the microphone close to me. Okay, so it's an ideal Rankine cycle with reheat and regeneration. The problem mentions a turbine 1, a turbine 2, and I believe just 2 turbines. So let's sketch those out. So we know we have turbine 1 and turbine 2. Reheat is mentioned, so that's most likely to be between the 2 turbines. We know we're going to have a steam generator always. We know we're always going to have a pump. Sometimes we have more than one. We know we're always going to have a condenser. So we're told that a fraction of the steam exiting turbine 1 is diverted to an open feed water heater while the remainder is reheated. So some of this goes to reheat and some of it gets diverted. We're told the fraction is Y prime, and we have a feed water heater, and we're told that it's an open feed water heater, so this flow will go right in and mix with other flows that come in. We keep reading that the remainder of the steam is reheated and enters turbine 2, and then no other mention of any other equipment at this point but a condenser, so we'll assume that comes from turbine 2 into the condenser. Saturated liquid exits the condenser and is fed to pump 1, so it sounds like there's going to be 2 pumps. We're describing it as pump 1. The outlet of the pump is fed to an open feed water heater, the same one that we had mentioned coming off of turbine 1. And then saturated liquid exits the feed water heater, fed to pump 2, and then returns to the steam generator, and then reason that it will come then to turbine 1 from the steam generator. We're told a couple things. Saturated liquid at the inlet to both pumps, and we're given temperature and pressure here. Let's call this state 1. We know this exit pressure, call it P2. We're told this temperature here, call it T3. This pressure here, P4. Saturated liquid here at the inlet to the pump 1. And then the open feed water heater, the pressure there is going to be pressure 2 because it's fed off of the exit of turbine 1, so the exit of pump 1 has to be at that same pressure and the exit of the feed water heater at that same pressure, so at pressure 2. So there we've got our schematic. Let's next do a TS diagram. And we have P1, P2, and P4. Those are our 3 pressures. Even though I skipped state 3, that's not another pressure. It's at the same, state 4 is at the same pressure as state 2. So I've got P1 at the highest pressure, P2 the next pressure, and P4 is the third pressure we encounter. And then coming back through the pumps, pump 1 we go from pressure 4 to pressure 2, and then pump 2, pressure 2 to pressure 1 again. So we'll start here. Let's label our states. So this is state 1, the inlet to the turbine, state 2 at the exit of the turbine, state 3 at the inlet of turbine 2, state 4, the exit of turbine 2, state 5 at the inlet to the pump, state 6 at the exit of the first pump, state 7 at the exit of the open feed water heater, and state 8 at the exit of pump 2. State 2, I'll label it again at the inlet to the feed water heater. So we have state 2 and 6 feeding the open feed water heater and coming out at state 7. So on the TS diagram we have state 1 here. It's isentropic. The problem says that all the pumps and turbines are isentropic. So we know it will expand in the first turbine, be a vertical line to pressure 2. So this is state 2 here. And then it gets reheated to some temperature. And then it expands again in the next turbine to state 3. And then goes into the condenser, follows this constant pressure line of P4 till we get to saturated liquid. It pumps up, or gets pumped up to P2, which is this line here. Follows that line, follows this constant pressure line, and then heats up to a saturated liquid in the open feed water heater, and then gets pumped up to, again, a vertical line straight up. So this is going to be state, actually this is state 3 up here, and state 4 down here. I skipped the reheat as a state. Then we're down to state 5, state 6, state 7, state 8, and then back to the turbine inlet. And the feed water heater, we also have some process here where we're mixing state 2 and state 6 to produce state 7. So there's my TS diagram. So I've got two isentropic processes. So we think through how are we going to find the different values that we need. Of course, I want enthalpies across the turbines to get my work. I want the enthalpy change across the pumps to get the power or work for the pumps. And then I have the steam generator. I want a delta H across the steam generator and a delta H across the reheat. Some of those H's are used for two different delta H calculations. So let's, for turbine 1, I'm going to need H1 and H2. For the reheat, H2 and H3. For turbine 2, H3 and H4. For the pump, H5 and H6. For pump 2, H7 and H8. And then finally for the steam generator, H8 and H1. So I'm going to need all those enthalpies to be able to calculate the efficiency or the power for each turbine, power for each pump, and heat transfer both for the steam generator and the reheat. So H1 will be a function of T1 and P1, so I can use the tables, the superheat tables, to find that. For H2, I'm going to use P2 and S2. And how do I find S2? Well, from T1, P1, I'll also look up S1 and find the specific entropy, And then S2 equals S1 because it's an isentropic process. Here, if we look at the TS diagram, we see that S1 and S2 are the same value, and S3 and S4 are the same value. Next, H3. H3 temperature is given. And we know that P3 is the same as P2, which we already have. And I could also write that S2 is the same as S1 here. State 4, I know the pressure, so P4, and I also know that S4 is equal to S3, and again, S3 I'll find from knowing T3 and P3. State 5, I know the quality. X5 is 0. And I also know the pressure or the temperature, but I'll say P5 equals P4. State 6, I know that H6 equals H5 plus specific volume in state 5 times P6 minus P5. State 7, quality is 0, and I know the pressure. P7 equals P2. State 8, H8 equals H7 plus specific volume, state 7 times P7 minus, or P8 rather, minus P7. And I know here that V7 is a function of T7 and quality 7, which is 0, and also that something else there needed. I guess P7 is the saturation pressure, but P7 is the same as P2. So we just have to be careful with units there. All right, so that gives me kind of a roadmap of how I'm going to find all the enthalpies. Of course, then we can go to the tables and start calculating all those things. But this really lays out all the thermodynamics, and the rest is just calculations and tables, except for finally then finding all the work. I'm going to capture this, save that, and then erase. I guess I can erase everything here. And let's start with turbine 1. The general equation is dE CV dt equals Q dot minus W dot plus, it would normally be summation M dot I, but since we have one inlet and one exit, H inlet plus V inlet squared over 2 plus GZ inlet minus H exit plus V exit squared over 2 plus GZ exit, since we have the same mass flow rate at the inlet and the exit. And I'm going to note that the velocity at the inlet and the exit are about the same, the elevation, the inlet and exit are about the same, so no change in kinetic or potential. It's turbine, so we're going to assume, well, we're told it's adiabatic, so if it's reversible, or if it's isentropic and we assume it's reversible, then it's also adiabatic. We'll assume it's steady state, so no change in energy of the control volume, no heat transfer, no change in kinetic and potential, and we end up with W dot for turbine 1 is equal to our M dot times H inlet, which is H1, minus H exit, which is H2. Now for turbine 2, remember we had some fraction y prime that was taken off, so we don't have all the flow going through turbine 2, so we've got m dot, but a fraction of that was taken off, so we're left with 1 minus y prime. If we resketch the turbine, here's turbine 1, we had some that was diverted, goes through the reheat, and then the rest goes into turbine 2. So if this fraction here was y prime, what's left is 1 minus y prime. And that continues through the reheat, that also continues through turbine 2, and then we had state 1, 2, 3, and 4. So I've got 1 minus y prime, again our total mass flow rate, which is what's given at the inlet to turbine 1, times H inlet, which is H3 in this case, minus H4. And then since we have the diagram here, let's jump next to the reheat. So for the reheat, we're trying to find the heat transfer in using our first law equation up above. We're saying it's steady state. There's no work for the reheat, and we're left with then 0 equals q dot plus m dot, and assuming that there's no change in kinetic or potential, we have H inlet, which is H2 minus H exit, which is H3. And if I rearrange things, I can write it as q dot equals m dot, but this is the m dot through the reheat, which again is our total m dot times 1 minus y prime. So what was left that we didn't remove to the feed water heater. And then since I left the Q as positive, I'm going to switch the H2 and H3, so H3 minus H2, since they're now on different sides of the equation. So that's my general equation for the reheat. So I've got T1, T2, and the reheat. Let's move on to the I guess the next two components we need to get are the two pumps. So let's okay, our last step is to go on to the pumps and the steam generator. So I've got coming out of my condenser at is a saturated liquid. I've got going into pump 1, and then that's going to feed my open feed water heater. And that's also fed by state 2 coming off my second turbine. So I've got state 5 here, saturated liquid, coming out at state 6, and then that feeds pump 2, which is state 7, and then comes off back to the steam generator, state 8, and then goes back into turbine 1 at state 1. So let's take a look at the pumps. My first law for pump 1 gives me m dot, but if you remember off my second turbine or into my second turbine in the reheat, I had 1 minus y prime, so that's still what's coming in here, the fraction of flow into pump 1. And then I had y prime coming in at off for the reheat between the turbine and the reheat. So I've got 1 minus y prime coming together with y prime, so it comes out as the total flow for the rest of the process. So my fraction of flow is 100% at those conditions. So I've got m dot times 1 minus y prime. Since the m dot I'm referring to here is the total mass flow coming into turbine 1, and then times the enthalpy change across the pump, which is H6 minus H5. And again, I'm putting the order of these, the larger enthalpy minus the smaller, because I'm calculating the positive pump value, so the work into the pump rather than work out by the first law convention. So this is the first law, but really calculating negative W. And then for pump 2, same equation, except this time I have the total mass flow. So according to the first law, this is negative work, but I want a positive value. And H8 minus H7. And then finally, the steam generator. So I've got heat transfer for the steam generator. It's going to be, again, the total mass flow times H1 minus H8. And then finally, the efficiency is the net work, which is the work for turbine 1 plus, or power for turbine 2. And I'm going to subtract the power for pump 1 because I reported as a positive value, but I know that the work from the first law is negative for that component, minus W for pump 2, and then divided by all the heat transfer. So I've got Q for the steam generator, and then plus Q for the reheat. And what students often forget is, although every one of these terms then has an m dot times delta H, the terms in the numerator, the percent of flow for the turbine 1 is 100%, but it's 1 minus y prime for turbine 2, 1 minus y prime for the pump, and then 100% for pump 2. For the steam generator, it's 100%, but 1 minus y prime for the reheat. So if you're going to just use delta H's rather than the actual calculated power and rate of heat transfer, you need to remember that all the delta H's need to be multiplied. So this would be just delta H, but this would be 1 minus y prime delta H, and this would be just delta H, but 1 minus y prime delta H, 1 minus y prime delta H, just delta H. So sometimes we write the efficiency in terms of all the delta H's, but then we need to make sure we have those fractions of the flow as part of the equation. And then just finally a concluding remark, when I rewrite the energy equation, first law, what I'm saying with the pumps is that, strictly speaking, if I bring the work to the left side of the equation, there's no change in energy of the control volume, or it's steady state. It's adiabatic, or Q is 0, Q dot is 0. Then when I bring the work to the left side of the equation, it would equal m dot times H inlet minus H exit. But you'll notice what I did in the equations for the pumps is that I used the power for the pump equals m dot H exit minus H inlet. And that's typical because I want, this would be less than 0 for the pump, and so this value would be greater than 0. So I would rather indicate the power in to the pump, which is this equation, and this is the standard convention for the first law, which is the work out of the system, or power out, and this is the work into the system. So generally you wouldn't give the negative work for a pump, but when we put it into the equation for efficiency, then I have to make note of that I need to not add all the power, but subtract the pump work since I made them negative. And you can do it either way. Leave everything positive, or leave everything as this first equation, and you'll get negative values for the pumps. You'll get positive values for the turbines, in which case when you're calculating the efficiency, you would add all the power terms. Some of them would be positive and negative. So the choice is you. I think the way I did it is more standard. I hope that helps. Take a snapshot of this. And you can go back and review any part of this. Of course, I left the calculations up to you.